So in this lecture, what we are going to do is see this whole whatever we have been seeing matrix and this multiplication, all the stuff from the eyes of a mathematician. So we'll see from mathematician's eyes, how does a mathematician see it. What I told you that mathematicians have tendency. So if you see the world like a mathematician, he'll find a structure in problems, and then what a mathematician does is he'll forget about the problem that they were solving. So there is a real world problem, some problem will be there. So but there will be a lot of other real world problems that will have the same pattern. So what mathematicians do is they generally see this pattern. Okay, this problem is like this problem is like this, and they'll find a certain recurring pattern there. So what they do is, irrespective of the problem they are solving, they'll leave it. And what will they do is they'll focus on this pattern, then solve this pattern now. And as a solution, they'll build a framework. Okay, they'll build a framework of solution. So that framework can be then equally used everywhere. Okay, that's what people generally do. While they, as a mathematician, they generally do this because they have real world problems, they want to abstract other things. So that's why today we will introduce vector spaces like that. The topic today will be vector spaces. Because we have seen a lot of like what this is a matrix manipulation, and then we have seen how do we perform multiplication. Now we'll see from mathematician's eye, how does a mathematician see the world of this vector space and why was the need of a vector space. So in order to understand this, okay, we will have to go into a bit of abstract algebra. Today's class might look a little dry to some people because it will not have direct implications, but I just wanted to show you that how a mathematician creates this framework. So in order to create this, we'll first introduce a term which is called as group. So what is a group? We'll see mathematically what do we call a group. So a group is one of the simplest algebraic structures. So there are different algebraic structures which mathematicians define. So among them, group is one of the simplest algebraic structure. So what it captures is, it captures the essential properties of like addition or any other binary operation, because you know that there is the operation, suppose multiplication can be operation, addition can be operation, and these are binary operations. So binary, I mean they take two operands and there is one operator. Suppose you have this 5 plus 2, so this is a binary operation over here because it takes two operands, and that is this operator will not work without these two operands. Now this group is that simplest algebraic structure which captures these essential properties or this addition, which generally this is written as addition like this, but it might have a different meaning than addition. Okay, and the definition goes like this. So you have this group, will consider it like G, and then you will be given an operation. So operation will be, suppose we can call it multiplication or we can call it addition, howsoever you want. So you will have some set which is G, okay, and then you will have an operation. You will have one operation which can be denoted the way you want. You can denote it like this, you can denote it like this. Majority times you will see that the operation is denoted like, suppose the star. Okay, I'll take the standard notations that generally are given in the books, so I'll stick to that. So now this is this group is a set together with the binary operation. So how do we do that? So G cross G goes to G. So this is how we'll do this. So with this operation star, this is the first thing that should satisfy. So what I mean by this is, because G will be a set and there will be some element, suppose small g, which will belong to this capital G. So if you perform this operation, suppose you perform this operation star on this, and even when you do this G dot G, it will suppose give you some value, let's call it F. That F should also belong to this G. Okay, that's by definition. So what is a group then? A group is an algebraic structure where we have defined this G with some operation, that is binary operation, and then with this definition it should also follow certain properties. The first property it should follow is associativity. And you know what associativity is. So if you have an element A and you have this element A, B, C, and then this should be equal to A, B, C, and then you can put brackets over here and brackets over here, because you can associate it. But now here the condition is that all A, B, C, they must belong to this G. So G actually here is a set. So you have this G as a set, and then you have defined this star as an operation. So this a set plus this operation will be called as a group if it follows certain property. So this is how you define the definition. The first property I told is associativity. The second property is that identity element. So what do you mean by this? Because last time once I was discussing inverse with you, I started giving you a taste of this abstract algebra. So there I told you, okay, this operation will be defined, based on that we'll define an identity element. So there is an element, let's call that element E, which belongs to G. So some element will be taken from this set G. So how should this E behave? So under this operation E, so E star A should be equal to A star E should be equal to A, where E and where this A belongs to G. What is the meaning of this? Pretty easy. So you have an element, some element E. So if it behaves like this element will be called as identity element. So as I said in the previous class as well, suppose if you take a simple addition, so in order to define an identity element there, and with respect to that plus operation, the 0 can be there, because 4 plus 0 is equal to 0 plus 4 is equal to 4. So that's what I'm giving. I'm just now giving the generic definition. The first thing that I told you, this G is a set and it is defined with the operation. Okay, the definition goes like this. Now with this, it should follow these properties. The first property is associativity, and the second property is that there should be an identity element, and the third property is it should have also an inverse element. Okay, most of these things have been discussed, but when we're defining the inverse of matrices. So here I am just formalizing them. How do we define the group? So again, here inverse element will be like this. Suppose you have this A which belongs to G. So you have an element A which will belong to this group. So there must be an element B which will also belong to this group. So you'll have an element B, and if you perform the operation, if you perform this A with this operation B, that should be equal to B, this operation A, whatever operation you call. You can call it addition, multiplication, howsoever you want to define. This should give you identity element. So then we will say that A and B are inverse of each other. So that means for all the elements in A, so if you take any element of A, so there should be some element B. So once I operate these two elements, so it should give me identity element. So these are three properties that we should have. We'll call that a group. So now what is a group mathematically? So a group is a set. You will have the set, and then you will have this operation defined. But operation should be binary operation. Okay, so we can write it like this: G comma star. And G comma star, one defined like this, if it follows these three properties, we'll call it a group. So now you can easily define it like this. So you'll say a G comma star is a group for star. When you perform this operation, suppose you perform G cross G, it should give you G, and then it follows these three properties, the three properties that I told you. So this is the definition of group. So then if in addition to this, it has one more property. Suppose if this operation is defined, if it has commutative property also, if it is A star B is also equal to B star A for all the elements. So where A comma B, this belongs to G. Okay, then we call this an abelian group. Okay, so this might look boring to you, but this is how a mathematician sees this, because we are now not worrying about the real world problem we are solving. We are just going into the abstract way of defining a framework that we'll call a linear algebra. So in that algebra, we have taken the first topic, that is vector spaces. So in order to define this, so what we had to do is we had to come up with a different notion of an algebraic structure, which is called as a group, and then we have defined a group. We have defined abelian group also. Abelian group is where this commutative property is also hold apart from these three properties. One where we have associativity, we have identity element, and we have inverse element. Okay, so what is the example of a group? Suppose if I take integers, if I take integers comma operation plus. So if you check this, so integers can be like -1, 0, +1, 5, 8, 9, whatever you take integers, and then you take this operation. If you check this, if you perform this operation on this, if you use this definition, the definition I have given over here, this definition, and then it follows associativity. Okay, it should have an inverse element, it should have an identity element, and in order to be an abelian group, it should also follow commutativity. So you will see that all these properties are followed by this. The Z and plus is actually an abelian group. Let's take an example. Suppose what is the identity element over here? 0 is the identity element. What is the inverse element? Negative of whatever you have. Suppose you have A, negative of A is the inverse element. So and if you see the associative property, you will see, you know that A plus B plus C will be equal to A plus B plus C, depends. Here you can associate it like this. So this is also followed, and you can see inverse is also there, and identity element is also there. So you can call this the integers, and with this normal addition operation, this can be called as an abelian group. Similarly, suppose if you have real numbers, okay, if you take away 0 from it, so okay, non-zero real number. So how do we write that mathematically? So you take this R, and then you take out the 0 out of that. So R without 0, okay, and then you define operation multiplication. This also is an abelian group. And you know what you have to check is, you have to check these three properties. You have to have four properties rather. Associativity, you have to have an identity, have an inverse, and it should be commutative with this operation. So if it follows, then we call it an abelian group. Okay, so now we have defined what a group is, what an abelian group is. Now we'll go to what a field is. Okay, there is a second algebraic structure which is called as field. Yes, we have a question. Yes, please. Okay, the second algebraic structure which we'll define is called a field. Okay, so what is a field? So now a field, basically it is a set which is equipped with two operations. So right now if you see a group was given one operation, suppose this star, or you can also call it plus, it depends how you define this. Okay, and now this field will be given, it will have this field, and we will have two operations. Let's call this plus and star. It depends how do we define these notations, but generally in the book standard notation is written like this. So there is a field is equipped with these two binary operations, like usually called as addition, and this is called as multiplication. That's why we have just and maybe they can be defined in other ways as well. Okay, they also like behave on the basis of rational real numbers, so you can add, subtract, multiply, divide howsoever you want. So now how is a field defined? So field is given with two operations, this f plus and this star. Now it should have two properties. So what is the property it will have? So you will have this f field. So you will have f, and with respect to this plus, comma this plus. So now if you can see, with respect to this plus, if this is abelian group. So you have two. Now initially you had a group. The group was corresponded with one operation. It was given with one operation, and you defined the properties. And now what I am saying is a field will be associated with two operations, this addition as well as this multiplication. So if with respect to this addition, this field elements, so okay, it will be a set of elements, and then this plus. If this is a abelian group, okay, and for this f, and if you subtract 0 out of it, and then with respect to multiplication, if this again is an abelian group, so you call this the thing a field. And one more property that holds that connects these two operations is the property of distributivity. So you should have distributivity. So the meaning of that, if you have a dot b plus c, so it should be distributed like this: a dot b plus a dot c. So this thing over here is called a field. Okay, the definition of field is this by definition. So if you have this field will be having a set of two, it will have a set of operations, this plus and this star. So this will be called as, say, addition, not a general addition, it will be called a field addition, and this will be called as field multiplication. Okay, and over here if you see, there will be two things. So field with respect with this plus, and field if you remove 0 out of that, and with multiplication. So this should be an abelian group, and this also should be an abelian group. And the third property it should have is that it should follow this distributivity, that is how to connect these two operations together. So they should be connected by this. So anything that follows this property will be called as a field. Okay, take an example, suppose of rational numbers. Okay, if you take rational numbers and give it two operations, if you take suppose real numbers, give it two operations, you can take different functions. Even here this can be a set of functions also. With functions you can define different operations, and you can define a field on that. Okay, now what we have done is we have initially defined a group for us, and you know how a group was defined, and from the group we defined what is called a field. Okay, so once we define field, now we are in a position to define a vector space. Okay, so what is a vector space now? So in vector space we have a field f. So we have this field f over which this vector space is defined. So we call this a vector space V. So we'll call a vector space V. Let's write it, vector space V. Vector space V is generally defined over this field f. Okay, so we have this f. So suppose any field, we can take any field, as you know that field is with operations. Suppose a plus, that is addition, and this multiplication. So now a vector space will be defined on this field. Okay, so what is the property that it will have? It should follow at least these properties. First is vector addition. Vector addition, that means suppose if you have this operation plus, and if you take any vector v, and if you take other vector v and you operate on this, so it should give you this v back. And the second thing is scalar multiplication. Scalar multiplication. Okay, I am sounding more like a mathematician now. So this is how mathematicians do it. So now what you have is, you will have suppose this dot operations. How is it defined? So you will take an element out of this field. Okay, and if you take a vector from the vector space, so v that would define, and it should give you another vector space like v. Okay, so this is generally defined. This thing over here, you might have seen this like this, u plus v. Okay, and here you could have seen it like c dot v. Okay, this is called c dash, and let's call this as v dash. Okay, so if you see now over here, this is called as property of closure. So why so? Suppose if I have a vector, so if I add these two vectors together, so whatever resultant vector I should get, that should also be in the same vector space that we have. So what is a vector space then? So vector space is defined over a field which follows these two properties. So which follows this vector addition and scalar multiplication, and it also supports some axioms. So with axioms I mean the v comma plus, this should be an abelian group. This should be an abelian group. So this is like axiom v, and then we have this c u plus v, and this c u plus v, it should follow distributive property, that is c u plus c v. Okay, I'll see if there are other properties. There are a lot of other properties. So this c plus d dot v should be equal to c dot v plus d dot v. Even I haven't memorized all the properties, I still need to refer to the book, but this property is very important. If you can have this vector addition and then can have, say, scalar multiplication, so you can sort of see these axioms directly follow from this. So if you have the c d dot v, so this can be c dot d dot v. So this cd can be multiplied like this. Okay, and one more property is if you have an identity element and then you take this v, you will get v out of this. So these are just axioms as a consequence of whatever I said over here. So but the most important property that you have to remember is the disclosure one. So if you take any vector from this vector space and you apply this addition onto that, so the element should still be present in this v vector space. Similarly, in case of scalar multiplication, if you have a vector and you scaled it up, so the scaled vector should still be present in the vector space. Questions? So I was just giving you the abstract definition of how mathematicians generally they'll decide on a framework. But if you see this looks quite verbose and this looks quite mathy. But if you have seen, we have discussed almost all the things. Let's take an example. Suppose we generally call, say we have a vector like this. You have 2, 3, a vector. Okay, and you have some other vector 4, 5. Okay, if I generalize it, suppose if I take these real values, I'll take real values over here. So I can call this vector as R2. R2 basically means a vector will have two components, one over here, one over here. So if I have these two things, then I have defined what is called as vector multiplication and what's called as scalar multiplication, and then we have this vector addition. So vector addition was defined like this, and scalar multiplication was defined like this. So and we have given definitions of vector addition. So if you have vector 2, 3 and you have other vector 4, 5. So how was this vector addition defined? So you have to component wise add them. So you say 4 plus 2 is 6 and 3 plus 5 is 8. This is how addition was defined. How was scalar multiplication defined? If you have a vector say 2, 3 and if you have scalar 5. Okay, so how was this defined? You have to component wise multiply this. So this will be 10, 15. Okay, so these are two operations that we were even without telling us like these are the underlying operations. So we were calling these things. So this R2 is actually a vector space. Now you can refine it through this through the framework that mathematicians have sort of developed to generalize the whole thing. Now we are not restricted to R2. As I said, this R2, this can be also a function. It can be a set of functions. It can be matrices. It can be anything that you have. So, but if it follows the same framework, so all the things that were discussed in this will certainly apply to this. As I said, we have a real world problem. Okay, let's come back again. So we have some real world problem. So there will be real world problem 1, some other problem, real world problem 2. They might look different. If you look at from the outside, they look different. But if you see, there is an underlying same pattern would be there, same underlying pattern. So if there is same underlying pattern, so how does a mathematician see it? He sees, okay, let's do this, let's cancel this real world, whatever implications it has, let's leave it. I see a same underlying pattern. So can I abstract it out? Can I now not think about the real world problem, rather than that I'll just create a framework? I'll create a framework. So whatever I define in this framework, it applies to this problem, it applies to this, it applies to all the problems. So in this case, majorly we are dealing with, suppose, matrices, and it can be functions also. Suppose in this case we had this R2, it can be a set of functions as well. So the thing that you can see over here, so this R, you have defined it as a field, and then you have defined a vector space onto it. So this is the definition that mathematicians will give you if you call it vector, if you have to define a vector space. What is a vector space? A vector space is V is defined onto a field in which these two properties should hold, and these are the other axioms that follow as a consequence of these properties that I just showed you over here. Okay, as I told you this, so suppose you have this 2, 3, 4, 5. Is this R2 a vector space? How can you check this? So you have to have these two properties. Let's take this R2. So now any element, so you can have element A, B over here. This belongs to any general element. So let's have this CD. So this is an element which belongs to R2, and this also belongs to R2. Now the first property that we have, can you add these two vectors? Yes, AB and this CD. Okay. Now if you see, if I add these things, I'll get A plus C, and over here I'll get B plus D. This A plus C, I know for sure it belongs to R. It belongs to R, and this also belongs to R. That means this whole thing belongs to R2. Why? Suppose this is a real number because this was belonging to R and this was belonging to R. So when I perform addition, I know that A plus C also will belong to R. Similarly, if I have this B and D, if I add these B and D, because this belong to R and this belong to R, I know for sure that B plus D will also belong to R. Now we have to see it for the multiplication. So if I have any vector, say X and Y, okay, if you take the C is a scalar multiplier. This belongs to R. Okay, and these two also belong to R. Now if you multiply these two things, so you'll get Cx and Cy. So if this belong to R, this belong to R. If this belong to R and this belong, for sure that Cx will also belong to R, this will also belong to R. That tells me that this R2 follows all the properties of vector space. That means this R2, given we have this addition the way we defined it and the multiplication the way we defined it, this is a vector space. And any element from this V is called a vector. Okay, we'll call this as like generally this over here will be denoted by V. So any element from this R2. Okay, so we'll have this R is a field. Let's call this R is a field over here. So we have two operations, plus and this. So V is a vector space which we have denoted like this R square. R square is our vector space. So what I'm telling you that it is following the properties that we have defined over here in the vector space. Okay, any element V belonging to this R square, any element, suppose V1 belonging to this R square will be called as a vector. Okay, any questions still here? This is all the things that we have already discussed, but the question is now, how does a mathematician see it? He abstracts all the real world details. He is not worrying about whether we are dealing with matrices, whether we are dealing with functions, whether we are dealing with something else. He just defines it in a way so that whole of these things which have the same underlying pattern can be handled by this. Okay, it can be functions also. Suppose you have this, you can let's denote V. So let's say V is a vector space. So we have some function, set of functions. They can be called like this F, and it goes from X to suppose some field F. Okay, so we can also define it like this, and then you define the operations on the function. So this again comes in the framework of vector spaces. It is not restricted to the matrix that we have seen so far. So that is why it becomes so powerful. Once you can extend right now, majority of the times we'll see it in terms of these matrices, in terms of these matrix manipulations. But you can apply the same framework onto the all other things. That's why it's called as linear algebra. Okay, so it's not just called as, suppose we have not named it as matrix or determinants. The thing that you have seen in your +1, +2, that people generally call this chapter as matrix and determinants, because you majorly study about matrix and determinants. So here we have called it as linear algebra. Okay, and linear algebra is because of that. Most of the examples that we generally take in this book is from the point of matrix manipulations. Okay, so we understand it from that perspective, but as I told you, you can take any functions, you can take any other structures which will sort of follow the same mathematics, and you have a framework. You can use that framework. You know, whatever was defined on this matrix, it will also apply to all the other things that we have defined which had the same underlying pattern. Any questions so far? Okay, so give me 5 minutes. I'll tell you the rationale behind introducing these things like this. So rationale is this, that once you get some problem, suppose you people will be researching in your field, so you will solve a lot of problems. So you solve some real world problem once, some other problems, and you solve some 5 problems. And what you found out is, after solving these problems, they have same underlying structure. Underlying structure is same. Okay, so you should be well equipped enough, and you should know that, okay, I found the same underlying structure. So can I think like a mathematician? Can I build a framework on this? Maybe there will be a lot more problems that will exist in reality, which will have the same underlying structure. So what I can do is I can create a framework. This framework will be equally applied to all these things. Okay, that is why this maybe half an hour or maybe an hour was introduced to you, so that you have this understanding. So it's not like there is something discovered for you. Suppose some maths is discovered for you, you learn about it and you learn the applications, and then you will become intellectually dependent. Okay, the thing is, you should not become intellectually dependent. You should have at least such wings which you can sort of spread, and you can see, okay, I know I have a learning algorithm beyond me. So if I found some problems of this sort where I am seeing an underlying pattern, so I can make a framework of this. Maybe you can, the framework, the things can be wrong in that framework, that then other people might come, they'll solve it with that framework, and slowly you will see that you will open a different branch of mathematics. As I was telling you people, that there is a separate subject in mathematics which is called as group theory. So where I introduce you to groups. So you see this, so this group theory is a separate subject. Okay, similarly, why we will discuss these fields, and you might have heard about like there's a subject called as topology. Topology also uses this group. So there's a different branch of mathematics. So once you create a new framework, so it is like you are having a ladder. So suppose you have to understand something, but you know the understanding generally is linear. Do not jump directly. So what will happen is, so this will be like later. Suppose you have to understand something, or you have to solve something like this, something over here. But if you are at this stage, suppose, and there will be missing links also. It's not necessary that all these steps will be made. So there will be some missing links. So you don't know how to jump from here to here. So what you sometimes might have to do is, you will have to find these gaps and you will have to connect these things by yourself. Okay, as a researcher, as a person who will be spending time in thinking, so you will have to develop these steps yourself so as to reach over here. So there will be a disconnect, as I said. So if you see this field of cryptography, so you can heavily see the usage of these groups. Okay, and you can even if in your pseudo random number generators, you can see rings and all these things are used. So that's the mathematical foundation that was already there, and then after that we could use it to solve some real world problems. Similarly, if you see number theory, so number theory did not have any real world application. After the coming of this cryptography, it suddenly found this found the way into the real world problem. So that's what I want you people to take out of this lecture is, so that if you solve some problem, you are having capability, at least you are having this thinking where you can easily come up with your own frameworks. Okay. Going beyond now, we'll take examples. Okay, from here now we'll discuss the examples of the vector spaces. Suppose you have this R2, we can also have this R3. R3 is the 3-dimensional space in which you will have vectors. Suppose 1, 2, 0, and suppose 4, 5, 0. 4, 5, 3, something of this sort. So these both vectors belong to this R cube. Why? Because you know that each entry over here, this entry, this and this, they belong to real numbers. Okay, and it has 3 components. So now how can you define addition and multiplication? Similar in the way it was defined in R2. Okay, and you can clearly see that the properties that we have seen, additivity and scalar multiplication, so that will be holding in both of these cases. So now let's take this. If we have this R2, if I subtract 0 out, if I remove the 0, so R2 basically means I have this. Okay, so I'll remove this, I'll have a hole in here, so that means I will remove this point. So what do you think? Is it still a vector space? Question for you. So question asked here was, is R square, if I remove 0 from it, if I remove this element from it, does it still remain the vector space? So if you create a hole in here, so what will happen as a consequence of this, because we have to check for 2 properties. The first property is because you have this R and then you have this field defined, okay, and then you have defined a vector space onto this R2. So R2 basically means you can have a vector of this sort, A and B, and these 2 operations will be there. So now what I can tell is, if you have this AB, what is the inverse of this? The inverse of this will be minus A, suppose minus B. If I take, if I add with respect to this addition, suppose. So this addition, if I add these 2 things, I'll get 0, 0. So now you saw that the closure property doesn't hold now, because I have this vector V1, I added at the vector V2, and I got a vector 0 vector. But 0 vector is not the part here. So this is no longer a vector space. This is not a vector space. Okay, why? Because we removed this thing. So because of this one, I showed you that one property got violated. Other property I can see, I have a vector A, B. So if I scalar multiply it with 0, so 0 is from this, 0 belongs to real number. Okay, and now if I multiply this with A and multiply this with B, I'll get 0, 0, and then I'll get basically 0 vector. So 0 vector again is not part of here. So the second property is also violated. So that means this is not a vector space. Okay, now what I can do is I can get some other vector spaces. So I have vector space R2, suppose. So I have this vector R2. This is my vector space. Let's call it V vector space. So we have this V as a vector space. Let's call it, there might be a subset W. Okay, a subset WV. So this subset can be called as a subspace. We have defined vector space. Let's suppose this R2 is a vector space. Let's call that V. So if there is something called as W, which is subset of this V, if it is closed under vector addition, similar thing. If it is closed, if W is closed under vector addition, the first property. The second property is W is closed under scalar multiplication. Okay, scalar. If these 2 properties are holding, that means this U plus V belongs to, suppose this is also belongs to W, and you have this U comma V, this belongs to W. Similarly, if the C dot V belongs to W, and given that this V also belongs to W, if these 2 properties are there, so we can call this W as subspace. Let's take some examples. Suppose R square. You know this R2, this is a vector space, and now R2 is a subspace of itself. Okay, this is a subspace. So what else can be done? Suppose if we take some line. So if we have this R2, one element can be 2, 3. Okay, 4, 5 can be other element. So now what I can do is I can say a simplest subspace of this is 0, 0. So if I take element 0, 0, so there is only one element in there. So I am saying this element, it only contains element 0, 0. You know that 0, 0 is a subspace. This is a subset of this vector space V, that is this R square, because it has only one element. So now if I add this 0, 0, if I add this with itself, so it will still give me 0, 0. The closure property holds. Okay, if I multiply it with anything, so I multiply it with suppose 5 multiplied by 0, 0, it will still give me 0, 0. That means it is holding both the properties. It is closed under vector addition, okay, and it's also closed under scalar multiplication. That means this 0, 0, it is a subspace. 0 is a subspace. Similarly, suppose if I take this, if I say I have some vectors, I have a vector 1, 4, I have other vector, suppose say 2, 8, other vector suppose is 3, 12. So what I'm trying to tell you is, okay, I have some vector AB and I'm multiplying it with some scalar C, any scalar C. So I have all these vectors. So now you know that these are subsets of R square, these are subsets of R square. Okay, so now what I can do is, if I can show you that this is closed under a plus and this is closed under scalar multiplication, so then I can also show this is a subspace. So how can we visually see it? Visually it should look like this. Suppose you had R2, this is the whole R2. Okay, this is your whole R2. So what is this set of vectors? This set of vectors is 1, 4. So 1 is over here suppose, and 4 is 1, 2, 3 and 4. So 4 looks like this. This is a vector. So because I am taking the scalar multiplication of this vector as a set of vectors, so set of vectors is this. So a line in this case. So this line which is passing through origin, okay, this is also a subspace. because you take any of these elements, you take any of this element. So you'll say 1 plus 2 is 3, 4 plus 8 is 12. So you'll get an element that belongs here. If you take any scalar and multiply it, you will still land here. That means this vector space, okay, this subspace which actually was made out of this R2. So this is subset of R2, and it follows both these properties. It follows the property of it is closed under a scale under vector addition, and it is also closed under scalar multiplication. So that means in this R2, any line which passes through origin, okay, is a subspace. So can you tell me, if I take suppose this line, if I take a line of this sort, okay, any vector of this sort, so do you think that this is a subspace? If so, why? If not, why not? So if you saw here, what I said is any line that will not go through the origin. Suppose this is not going through the origin. There is a simple problem here. Let's suppose this line is somewhere. This line is say t comma say 2t, something of this sort. Any line, it can be any line. So now if I multiply it with 0, so this will become 0 comma 0, and this is the 0 comma 0 vector is not lying on this subspace. So it is not an element of the subspace. That means a line which is not passing through origin is not a subspace. Okay, all the lines in R2, because you have this 2D plane. This is very important to understand. If you understood this, because we have to sort of project our thinking in the higher dimensions then. So R2 was our plane. Okay, any line passing through the origin, so that was a subspace. Any other line was not a subspace. So what is the smallest subspace? The 0 0. The origin itself is a subspace. But let's say in 3D. In 3D, if you have this, you have three dimension. So how is this a vector space? Because we defined it as R cube. Okay, it is like this. So you have 4, 5 and 0, something of this sort. So now if you see this, obviously R cube is itself the subspace of itself. But what I can do is, if I take some elements, I will take this. I'll take 1, 4 and 5. Okay, this is one element. And if I take some other element, say I'll take 6, 9 and 2, these two elements. And if I take all the linear combinations of this, so what will happen? So this will be a 2D plane, if you can think. Okay, some vector, suppose this vector is pointing in this direction and other vector is pointing in this direction. If I take all the linear combination, if I multiply suppose this with 0, this with 0, that is basically what is the meaning of this. C dot v1 plus suppose c1 dot v1, c2 dot v2. These are two vectors, and you can take linear combination of these things. So what will happen is it will have a plane of this sort, because it cannot go out of plane, because this is giving it the access to one dimension, this is giving it access to other dimension. So now you have a vector like this. So why is it called a plane even? So if I have a copy or something over here, let me see. So suppose if you see this, okay, so if I draw a vector on this line, on this, and if I draw a vector on this, I can span the whole thing. So you have heard about the word span. So if I have a vector over here, if I have the vector over here, okay, so what I can do, if I take any combination, it will be stuck on this plane. Okay, it will be stuck on this plane, but it can span the whole plane. So that's why I am telling you over here. So if I have this vector, I have this one vector, I have this second vector. So now if I take any linear combination of these things, so this will be like this. Okay, so that will be plane, and this plane will also go through origin. So this is a plane. So in R cube, so we have this plane going through origin. Plane going through origin. So it's a subspace. It is a subspace. So why is this so? Because if you take any vector, so you have this plane defined now. Let me make it a little bit detailed, a little bit bigger also. So this is your 3-dimensional coordinate system. So if you take two vectors, so somehow let's suppose this goes through origin like this. So this is your plane. Okay, so here is the origin and this is the plane that it goes through. So if you take any vector, suppose you had this vector and you had this vector which were lying on the plane. So this vector was there and you had this vector. As a consequence of this, you got this plane. The whole plane was because of this. So if you take any vector, because origin is here, so you are getting 0 0 vector also. So if you take linear combination of any of these two vectors, so this will span this whole plane. Okay, so both the properties, the property that the closure property is in terms of vector addition is still there. Okay, and in case of scalar multiplication is still there. Suppose you can scale it up. You can scale this vector, it will still lie on this plane. You can scale this vector, you can scale this vector, or you can take a combination of vector which will suppose land over here. It will not go out of this plane. That means this is a subspace. A plane in 3D is a subspace, but it must go through origin. So what is the one more subspace here? If I have a line, if I just have a vector, I have 1 3 5. Okay, if this is a 3D, so I saw that plane can be a subspace in there. But if suppose you take this origin and you have a line of this or 1 3 9 and it goes like this, it passes through origin. Okay, any line passing through origin is also a subspace, because it will have both the property, it will follow both the properties. The first property is that in case of vector addition, it will show the closure. So if you take suppose any vectors from this, so because you have single vector, so what you can do is if you have this vector and if you multiply it with itself, if you add it with itself, so you will get 2 times of this vector, that will still remain on this line. Or if you scalar multiply it with any value, suppose you multiply it with value a, so you will get a times 1, 3 times a, and suppose this is 5 times of a, so it will still be stuck on this line. So that means both the properties are holding. So this also is a subspace. So in case of R cube, okay, if you take a plane which is going through origin, that's also a subspace. If you take a line, that's also a subspace. And if you take suppose origin 0, 0, 0, that's also a subspace of these two things, this R cube. Any questions so far? Suppose I have this, I have a subspace, suppose I have vector space V, this is my vector space V. So I have subspaces, let's call them U and W, U comma W, they are subspaces, of V. So can you tell me, if I take union of these, if I take U union of W, is it a subspace? If I take union of U intersection, basically initially I'll take union, second time I'll take intersection, these two things, so which of them is a subspace? Which is a subspace and why? I'll give you 5 minutes to think. So answering this question is, so if you have this U and V, so the answer is not a subspace, but this is a subspace. Let's see the explanation why. So I'm taking a simple example. Let's take this R cube. So R cube is your 3-dimensional space. So you know that any plane passing through origin is a subspace. So I'm taking a plane like this, which is passing through origin, and then I'm taking other plane which is perpendicular to this plane, but it's also passing through origin. Now what you can see is it is like cutting it in the middle. So if you have an element U and that belongs to this U and W, we have that belongs to this capital U. We have this element, suppose this red portion, and then there you have this blue. So you have V or W, small w, that belongs to this W. You have these two vectors. If you add these two things together, U plus W, okay, so it will neither lie on this U nor W. Why? Because they are perpendicular to each other. So it will be somewhere in the middle. So that will be, so if you see it is like this, okay, so it is like suppose sort of like this. You take a vector from here and you take a vector from here, so it will lie somewhere in the middle. So it will come out of these two planes. Okay, so that means this will not necessarily belong to U and U union W. Okay, that means this closure property is not holding. If the closure property is not this addition, scalar, or I can say vector addition is not abiding to this closure property. So that means it is not necessary that if U is a subspace and W is a subspace, and if you take a union of these two things, it's not necessary that it will be a subspace. So that means the first thing is not a subspace. The second thing, while you are taking these to U and V and you are taking intersection of this, again take the same example. So if you take any of these, any of the two subspaces which are having which are meeting somewhere, say you have this R3, you had a plane of this sort, okay, and you had other plane also. Okay, you had other plane like this red plane is there. Okay, but where is it intersecting? It is intersecting on this line. The intersection part is this line. So this line is also a subspace. So by this I mean, suppose if you have a vector U which belongs to this capital U, bigger U, the subspace, and if you have a vector W which belongs to W, okay, that means if you take intersection of these two things, if you take U intersection of W, you only take the vectors which are present in both U as well as V. Now you have no way of coming out of that, okay, because all the vectors will lie on that. Okay, if you add these things, you will still be on that line, or rather you will be still on that intersection. If you perform scalar multiply, you will still be stuck on that. That means this U intersection V, this will always be a subspace. Okay, these two things are very necessary. Suppose now if I am giving you some R10 dimension, I am telling you that we have some 10 dimension which you can't imagine. Okay, and what I am telling you is I am taking a 5 dimension R5. This is a 5-dimensional plane which is going through origin. So somehow, because we cannot visualize it, but mathematics gives the tools to still compute. R10 is something which is a 10-dimensional plane. So there will be some 10 vectors which will span through 10-dimensional plane. So this R5 will be, there will be some 5 vectors, some 5 distinct vectors which are linearly independent. Okay, we'll have 5 vectors, suppose something of this sort. So if I take some 5 vectors out of this, so say I'll take this, I'll say we have 10 vectors. If I take some 10 entries over here, so I'll take 10 different vectors. You know that all these 10 different vectors will span the whole R10. But if I take only 5 vectors among them, I'll take suppose 10 entries. One is suppose this 1, 0, 8, something of this sort, first entry. I'll take such 5 vectors, okay, which belong to R10. So I'll just take 5 vectors. If I take the linear combination, so do you get that it will be stuck in R5 plane This is what you have to imagine. You have to at least act that you are understanding this point, because you can't imagine it, but you have to mathematically see. Because I'll give you an example. Suppose we were in R3. So R3 was, so we had three vectors. Suppose 1 0 0, some other vector 0 1 0, some other vector say 0 0 1. So now you know that if I take a linear combination, it will span this whole R3. Now what I can do is, if I take only these two vectors, if I take some two vectors which are linearly dependent, so what will happen is they will give me a plane. So these two vectors, because what is happening right now, so we had three axes like this. So I had a vector which is like this, I had a vector which is like this. So if I have only two vectors, so if I take the linear combination, so I'll be stuck on the plane. It is like there is an ant, so ant can either go up forward, and it can just come on the plane. It cannot open the depth of the dimension if it is not curved surface. So what I'm telling you over here is, you had this one vector, you had other independent vector. So if you linearly combine them, so what you will get? You will get this plane. Okay, so it actually, you require three independent vectors in order to show this R3, but you only had two. If you took linear combination of that, you will be stuck on this plane. Similarly, now beyond the imagination, just extend your thinking. So you are in R10, so you require 10 distinct vectors, 10 linearly dependent independent vectors, by the help of which you can construct this space R10. Suppose if I take 5 vectors, that means if I take 5 vectors which are linearly independent from this R10, so if I take all the linear combination there, all the linear combination, don't you think that we will be stuck on some that 5-dimensional plane? So how many of you could visualize it? I am on purpose not writing the code, because the first thing is, I cannot write the code for this, and there's 5 and 10 vectors. I could have at the most written code for this, but I want you to visualize that you have 3D. If you have only 2 independent vectors, you have a subspace, but that will be a plane. Now if you have this R10, so R10 is some 10-dimensional plane. It is some 10-dimensional vector space. But if you have only 5 independent vectors, okay, so when you take linear combination of that, you will be stuck on a 5-dimensional plane. How many of you understood this? At least try to visualize. Now that you understood it, at least you have tried to visualize, and then you had formed some notion. So if we had something, we can think of different subspaces. So right now our imagination only supports us till say R3, so we can have 3-dimensional space. Say if we have 2 independent vectors, and that will span sort of a 2-dimensional plane, but we can at least pretend to think that there is this R10 which is some 10-dimensional space, and if we have 5 independent vectors in that, so it will span the whole 5-dimensional space, and that we can't imagine, but we have to pretend that we understood it. Now let's come to the consequence of what is happening because of this subspace and these vector spaces. Now we have this equation, you know this, Ax is equal to b, you know this. Okay, this is a fundamental problem in linear algebra. So this is the central problem that we are trying to solve. Now what you can do is, if you are given a matrix, you are given, suppose you have some equation, some variable, so you are given 4 5 6, and then you are given 3 2 1. Okay, this is what you are given, and then you are given say x1 x2, then you are given this is equal to some say b1 b2, something of this sort. Okay, some maybe b1 b2 b3, b1 b2 b3, because if you see this matrix multiple, this is 3 cross 2 and this is 2 cross 1, so this will be 3 cross 1. So now the question is, will solution exist? Will solution exist always? Okay, now we'll try to visualize it again. Now you see this. So this is a vector, this is a vector. So multiplication is taking a linear combination. So what is this each vector is from? So actually if I had all the vectors, so this is from R cube. So 4 5 6. So it is from R cube. Okay, this 3 2 1. This is again from R cube. So that is, it is a this is a vector. This is a vector space, and this is a vector from the vector space. Now what you are trying to do is, you are trying to take linear combination of these. This x1 and x2 basically means take this and take this, combine them somehow. Okay, so can we land it at b1 and b2? So this basically means you are in R, you are like something of this sort. You are at this. So you had these two vectors. You had vector 1 of this sort, and you had some other vector, vector 2. So now if you take all the linear combinations possible, so what will you come up with? So you will most probably have this plane. So you'll have a plane which is a subspace. Okay, and this will be the plane. All the vectors that are reachable, all the vectors that are reachable from these two things are the plane. So if this, because now you know that this also belongs to R3. Now this can be out of this plane also. This can be, this b vector can be out of this. So b vector can be out of this plane. It can lie out of the plane, or it can lie within the plane. So either it can lie on the plane or it can lie within the plane. So solution will only exist if this b1 b2 b3 it lies on this plane, on the plane. So how many of you understood this? So the solution for this equation, so if you have this equation, okay, and you want to find the solution b1 b2 b3, you want to find such values of x's such that this is b1 b2 b3 should be the should be given as an output. So what I am telling you is, so now you know that this belongs to R3, this also belongs to R3. Okay, so now in this R3, So now if you take these two vectors, if you linearly take all the combinations, so it will span, it will have this plane as a span. So if this b1, b2, b3, if that is present on this plane, then only we will have some linear combination, we will have the values of x1 and x2, otherwise there will be no solution. So how many of you understood this? So now that you understood it, if you understood it, this thing over here, so all the combinations, suppose you are taking this x1 and x2, so this will give me a combination of this, whatever vectors I have taken over here. This was 4, 5, 6, 3, 2, 1. So 4, 5, 6, 3, 2 and 1. So I was taking all the combinations and I was trying to check if this b1, b2 and b3 are reachable. So if this is reachable, I am telling that yes, there will be a solution, otherwise there will be not a solution. So whatever vectors are reachable from these things, this is called as column space. C of A, suppose this is my A vector. So I'll call this as a column space. And column space is also a subspace. This is a subspace. So how do we define column space then? So column space, basically if you have this AX is equal B, so this A is the coefficient matrix. So you are checking the span of this A. You are saying whatever is reachable from A. So if I take linear combination, any combination of A, so whatever vectors we have there. So it will give me some vector space. It will give me some vectors, suppose some vectors, set of vectors. Okay, this vector is also a subspace and you can check that also. Okay, this is a subspace. So this is called as column space. So column space of A is this. So if any time you're asked what is the column space, you're telling that okay, give these, like if you take this coefficient matrix and you take columns of this and you take linear combination of columns, that will give you span of those. So whatever is the span of columns of coefficient matrix, so that is called as the column space. So right here, if you see, this is the column space. So if you had these two vectors in 3D, so this plane going through the origin, this was a column space. The column space is actually a subspace. So how many of you do agree that column space actually is a subspace? Okay, take an example of this sort. So you have this A and multiplied by x. So this it can be easily written. Suppose x1 a1, okay, plus x2 a2. So you have the first column. So you have this a1 over here. You have this a2 over here. Similarly a3 over here. Okay, then you have something of this x1, x2, x3, and so on. So now I am writing it in expanded form. x1 a1 plus x2 a2 plus x3 a3 and so on. Suppose some x and an. This is how I can write it. Okay, if I can just maybe enclose in a box. So this, if you see, is actually a linear combination. This is a linear combination. This is a linear combination. Or this is the span of A. This is span of this. Wherever these columns can span. So what I can say is this column span of a column space of A is equal span of, this is span of what, vectors a1 till an. Okay. So what is the property of this? The first property is CA is a subspace. Okay. This is the first property. And it consists, suppose all the vectors. So the second property that I told you, it contains all the vectors. Suppose ax is equal b, and this contains all these b vectors where we can solve the equation. So where this is solvable. So all these b's will be on that. Wherever you can find such x's, so you can find some solution to this x. So these b's will lie on that subspace. Okay. Any questions so far? Any questions on this column space? Any questions? Suppose if I take a matrix, suppose if I take matrix 1 0 0 1, okay. So can you say that if I take this matrix, suppose this is my matrix A, or we can call it any matrix, suppose A Z, whatever you take, I have this AX, so this is equal to some B. So given this A, so what do you think? Will this be always solvable? Suppose this X is where X1 y, this is like this 1 0 0 1, and you have X1 X2, and this is B1 and B2. Will this always have a solution? Will this always have a solution? What do you think? I am giving you a minute or so. Okay, so what Sajid said is, suppose if you have this vector, this is other vector, so you can think of as these two columns, and these two columns, if you see, are linearly independent. So if you take a linear combination of these two columns, so it will span the whole R2, it will span the whole vector space R2. And this vector over here, that the B vector, B1, B2, this vector belongs to R2. If this is spanning to the whole vector space, that means it anyway will it will be reachable from these two vectors. Okay, so that means C of A, the column space of A over here, is whole R2. So there will be always a solution. Any whatever you give, so we can give a solution if you are giving me an equation of this sort. Okay, let's take this example. So if I take suppose some three vectors, say I'll take some y vector 1, 2, I'll take some vector say 4 and 1, I'll take a vector 5 and I'll take vector 6. Okay, let's take one. Let's take one more entry so that it becomes more interesting. So this is 0, this is 3, this is 3. So what do you think? So in this case, if I take some x1, x2, x3, okay, and if I take say some b1, b2, b3, so what do you think? Will this have always a solution? The answer that we received is that we have to check that if these three vectors are linearly independent. So if these are independent, how can we check that? So the first thing is we have to establish this fact. Okay, if we establish that, that means if yes is the answer, then for sure this will have solution for every b1, b2, b3. Because if it spans the whole R3, that is why if they are linear independent, it will span the whole R3. If it spans the whole R3, this belongs to R3. That means there will be always a solution. If they are linearly dependent, suppose if no is the answer, that for some cases this is not the case. So that time what will happen is it will either span R2, okay, if there is a dependence, or it can sometimes span R1. But here I can clearly see two vectors at least it will span at least R2. Okay, it will not span R1 because you can see that all these vectors are not they are not dependent on each other. If it was like this, suppose I had 1 1 1, 2 2 3 3 3 3, something of this sort, then I could have said that it will just span R1 because it will be a line, it's a linear thing. But here I can at least see that these two vectors are independent. That means at least we can get R2 can be spanned. If other vectors also, if you take all the things and you see that they are all of them are linearly independent, that it will span R3. So for sure it will span R2. But you had checked will it span R3 as well. So that will be established once you know that it is all these vectors are linearly independent. So how can we do that? We can use Gaussian elimination. Okay, so there what will happen is if suppose a column of that becomes 0, so we can call that okay. So somehow we have removed that. It means that that vector probably was dependent, and if there are only two columns left which are independent, then we can call that it will span R2. So the only the vectors which will lie on that R2 will be we can find solution for that. For all the others we cannot find solution, and the concept of rank comes from this. So if you see, so if we have something of this sort, 1 1 1, 2 2 2, 3 3 3, you will see that because all of these vectors are dependent on each other. So these can be just replaced by 1 because what they do is they'll span this linear line. So actually these vectors are from R cube. Okay, so if the maximum rank should have been 3. Okay, but what can be done is you can see because they just span a line, there is a subspace that is line which they are basically spanning. So we can call the rank is 1. We will formally establish, but I am just giving you the hints what we are going towards. So now we can see that. So in order to check these things, we have to again use the Gaussian elimination. So we have to again see how can we do this AX is equal to B. This AX is equal to B, you know that how can we do that? We can use Gaussian elimination by that. If we somehow got one of these rows, suppose we got one of these column vectors were 0, or one of these column vectors can be seen that they became equal to other column. So we can say that only for some of these B's, so wherever you have this column space of A, so whichever subspace it spans, okay, so for only those B's which lie on this subspace will have the solution, otherwise it will not have the solution. Any questions so far? So we have studied what is a vector space. That was the first thing that we studied. We saw from the mathematician's eyes what a vector space is. Then we tried to establish what a subspace is. Then we saw a very important subspace, that is this column space, and we saw its physical implications also and its geometric implications. What is a column space and why is it a subspace? Okay, now in the next lecture we will go to what is called as a null space of A. Okay, so these two things are very important subspaces. So null space, so here we are trying to get the solution AX is equal to B. So null space, we will take care of this, AX is equal to 0. Okay, we'll define this null space probably in next lecture. So if you have any questions, I'll take them right now. So we have been starting our if you see our previous lecture, so we started our discussion with vector space and then we were discussing subspaces. Okay, so in this subspaces we have seen a very important subspace that was called as column space. Okay, column space, what does it mean? So we represent it as like this, C of A. So if you see what this means, so if you have any matrix of this sort, so you have columns in that matrix, C1, C2, C3 and so on. So column space is the linear combination of these columns. So we can say alpha 1 C1 plus alpha 2 C2 plus alpha 3 C3 and so on. Okay, so this is called as the column space, and we saw the implications of this column space as well. So today we will take another subspace which is very important, which is called as null space. So what is this null space now? Let's see, let's take a matrix A. So you know that every matrix basically is a linear transformation. So this is a linear transformation. Please be attentive, ask as many questions as possible so that we can have a thorough discussion on this, because it's very important from deep learning and machine learning perspective. So you have this A is a linear transformation. So what's the meaning of linear transformation? You have a vector in the vector space if you just focus on one vector. So once you apply this A onto this, so what we call as matrix multiplication, it takes that vector and that vector lands at somewhere else. So what we can see is if we can keep track of all the vectors, okay, and then we can see some special vector. So if there is this matrix A, and if it is multiplied with some x vectors, so can I do one thing? Can I have a look at the x vectors such that those vectors, the x vectors in that space, they go to 0. Okay, so what I'm telling you is, suppose we will try to visualize it in 2D. So you have a bunch of vectors. Suppose every point in here is a vector. So if I draw these points, there will be infinite points. That means there will be infinite vectors. So now you have these points in this R2, that is a real 2 space. So now what you can do is you can have any matrix A, okay, and then you can see if I multiply this whole vector, if I transform this whole vector space, and I'll see where are the vectors landing. So there will be some vectors. Suppose this vector, maybe this vector, maybe some other vector, some vectors. Okay, what they can do is once you are transforming them, they can land at this point. That means they'll shrink. So these vectors initially, this vector was suppose at this place, this vector was at this place, this vector was at this place. So you had multiple vectors. So once you apply this A transformation, that's this linear transformation. So what might happen is that some vectors which are very special vectors, so they will sort of get shrinked over here, okay, by the help of this transformation. So all those vectors in which this A is applying, or you apply this A on these x vectors, and those vectors are taken to 0. So those vectors are called as null space of A. Why is the first question is, why is it a subspace? Okay, why is it a subspace, or why is the vector space in itself? You know that how to check that. You have to check if it should be closure under scalar multiplication addition. So let's suppose we'll take this vector. So you have A v1. Okay, that goes to 0. That means this v1 belongs to null space of A. Why? Because this A takes the v1 vector towards 0. So once you apply this transformation A onto this v1, so this v1 will land at 0. That's the meaning of this expression over here. If you have another vector, suppose v2, A v2 is also equal to 0. That means if you have this v2, so if you apply this A onto this, that is you apply linear transformation onto this v2, this also is landing at 0. So now you know that if we add these two things together, so that means A v1 plus A v2. Okay, so if you add these two linear transformations together, so you know this is equivalent to A v1 plus v2 because of distributive property of matrices. So you know this is also equal to 0. That means if you add these two vectors, so you had one vector first and you had second vector. The first vector was going to null space of A. v2 was also in the null space of A. Now you added these two vectors. So once you added these two vectors, so now you know that once you apply A onto this, this will also go to 0. That means if v1 belongs to null space of A, and if v2 also belongs to null space of A, that means if you can add v1 plus v2, it will also belong to null space of A. The proof is quite simple. That's over here. So you have this A v1 is equal to 0, A v2 is equal to 0. That means A v1 plus v2. So it can be written like this: A v1 plus v2. This is also equal to 0. So this is the proof that this vector is a subspace or a vector space. So null space is a subspace. So what is not a subspace actually? I'll show you what is not a subspace. So if you have suppose Ax is equal to B, something of this sort. If you have this, so now if this is Ax is equal to B, so we have to find such vectors x where it goes to B. So can we say that this is a vector space? Can we say that? The easiest question is we can't say this is a vector space. Why? Because suppose we'll take an example. So this B is non-zero. So you have this A some matrix. So you had this x1, x2, x3, something of this sort, and then you have this say b1, b2, and b3. These are non-zero values. Okay. So if these are non-zero values, so if I am telling you, okay, can I take this x vectors which will land at this B, all the solutions basically of the equation, do they form a vector space? So the easiest check is, because 0 is not there, so 0 vector is not. If I say A multiplied by 0, this is equal to 0, this is not equal to B. Okay, so if 0 is not there, that surely means that this is not a vector space. This thing is not a vector space. So if you just have Ax is equal to B, you are saying all the solutions of this equation, that is values of x, okay, are they a vector space? They are not a vector space. The easiest answer is because you cannot have a vector space without 0. So in this equation, if you see, if you put x is equal to 0 and A is dot 0 is 0, and suppose you have this 0 is not equal to B, that means 0 is not in the in that space. That means that space is not a vector space. So that's why we have these special things. We have this column space C of A and this N of A. They are vector spaces. Why? Because 0 is there. So in null space, in column space, you know, AX is equal, suppose B. What is the column space of a linear combination of this? So linear combination basically means you can have 0 as a linear combination. You can have 0 times C1 plus 0 C2 and so on. So this 0 vector is there and it follows the properties of a vector space. Similarly, in this null space, you know, any vector AX is equal to 0, any vector that is taken to 0 is a vector that belongs to the null space of this. So why is the subspace? Because if you see, if you take any two vectors which belong to null space and if you add them or if you scalarly multiply them, you will see that they belong to null space, and 0 vector is also part of that. So if you take 0 over here, A dot 0 is also equal to 0. That means the 0 is part of null space. So this is the definition of null space. Any questions on this? So if you see how it is formally defined, it is only defined as this. So you have A is a matrix which is M cross N. So this is your matrix M cross N. So they are of real numbers. So how is this null space of A defined? So null space of A is defined like this, and it's written as null space of A is a set of all vectors. It's a set of all vectors. Now you know that if this A is M cross N, so what will be the length of the vector? A single vector if you take, so what will be that? So X will belong to, that is, so if X belongs to N of A, so that means X basically will belong to R of N, because you have this number of columns over here is N. So that means it has to follow this AX is equal to B. That is why this restriction is there. So this is the formal definition that you can write. I have not written the English, you can fill it in the English, so I'll just read it out. If A is a matrix which is of M cross N dimensions, the null space of A, which is denoted by this N of A, this is a set of vectors, so X which belongs to this Rn, such that it satisfies this equation, AX is equal to 0. Okay, and a null space is a trivial thing, it must contain 0 vector. Okay, that is necessary there. If you have to see, if you are given some bunch of vectors and you are told that is it a vector space, so you must see that, or it's a subspace of something, so you must see that this 0 vector, there should be the concept of 0 vector there. Okay, moving ahead. Okay, let's now see like what is the meaning of this null space, how can we compute this, and then we'll see is there an algorithm which will help us to compute this null space. Okay, let's take an example. Let's take example A. This is a linear transformation, a matrix. Let's take this is 2, 0 and 0, 3. Suppose this is our matrix A. So we have to basically say AX is equal to 0. That means what are the vectors which are taken to this 0. So all the set of vectors, once you apply this A onto these vectors will land at 0, the origin. So now let's start with that. So this, if you see this equation, so it can be written as 2, 0, 0, 3. Underneath everything is basically set of linear equations x1 and x2, and this is equal to 0 and 0. So if you expand these things, so what will happen? You will have 2x1 is equal to 0 and 3x2 is equal to 0. So you will see here x1 is equal to 0 and x2 is equal to 0. So there is a solution which you see this. So that means you already found the solution over here, and you saw that x1 and x2, both of the values should be 0. That means this null space of A over here is a 0 vector. Null space of A is directly 0 vector. Okay, so the rest of the things don't go to 0. So if you see this matrix over here, it takes only 0 to 0. Okay, rest of the vectors are taken somewhere else. That means null space of this A is only this 0 vector. Okay, let's take another example. So we'll build slowly on the example so as to give you the notion of how can we find this null space and why is it important. And basically, what does null space do? If you see geometrically again, so in terms of deep learning, say A is a huge matrix, and if there are some values that are taken to 0, that means it is erasing information. It is erasing the information. You see it from the deep learning perspective. Suppose you have a whole bunch of you have a huge matrix A, and in between layers, you know that you have this weight matrix which you apply onto. Suppose you have this pre-activation, activation. You know how the forward pass works. So now, if you have some vectors in there, and once you apply this A, once you perform that matrix multiplication, you know that you can see it as something of this sort. So you have a vector, you have a matrix which is full of these columns, and then you have other matrix which is getting multiplied with each other. So now there will be some vectors which are taken to 0. That means, so all the vectors which belong to null space of this A, that means you are erasing some sort of information. Or if you see in dropout, so what is happening in dropout? So you deactivate neurons on purpose. But there, this A can be thought as a loss of the information, and it can be good, it can be bad. It depends on how your network is being trained. Suppose if most of the vectors or all the vectors, suppose maybe we cannot say all the vectors, say most of the vectors, they belong to null space of A. That means this A matrix that you have is sort of degrading the information. It is taking every vector towards that 0. Okay, all these vectors belong to null space of that. So if you have a matrix A such that most of the vectors once multiplied with it are taken to 0, that means this A matrix probably needs to be changed. We need to do something about it. Okay, there is a problem in the network. Similarly, you can see, okay, one matrix that will take everything towards 0 is 0 matrix. So if you have a matrix which is all the entries 0, suppose you have this matrix, so any vector that you have, x1, x2, x3, any vector that you have, it will take it to 0. So that means A x is equal to 0. If we take any x, so if this A is all zeros, that means this is sort of erasing the information. So that is why all the vectors that ever you whatever you feed to this belong to the null space. So if you have, say, this A belongs to R cube, so you have this matrix in which each of the column that is there, say column of this, so you have C1, you have C2, something of this sort. Okay, you have C3. So C1 belongs, suppose, R cube. So all of these column vectors, they belong to the three-dimensional space. So if all of these are 0, okay, that means the 0 matrix. So where you have all the entries as 0. Now you know that this erases all the information. All information is erased. So what can you say about what is the null space of this? What is the null space of such matrix? What is the null space of A0? Let's write it like this, A0. So for the null space is whole R cube, because all the vectors that are there in R cube, they are taken to 0. Okay, you can think it geometrically like this as well. Okay, so now we'll take second example. Second example goes like this. Suppose you have this A. This is 1, 2, and say 2 and 4. So this is our second example where we have the first row is as 1, 2, and second row is as 2, 4. You know, it can be written as like this, 1, 2, and 2 and 4, and then x1 and x2, and this is equal to 0, 0. So basically we are solving Ax is equal to B. That's how x is equal to 0. That's how we will get to know what is the null space of A. That is, what are the vectors that go to 0, that they're taken to 0 rather by this matrix A. So if you expand this, so you get x1 plus 2 times x2. Okay, so this multiplied with this multiplied with this, and this is equal to 0. And second equation is, say, 2x1 and this is plus 4x2 is equal to 0. These are two linear equations. Okay, you know that this is the matrix representation. How do we solve this? You know how do we solve it? So you easily can see that if we apply on this, if you apply, say, Gaussian elimination, you can easily see that what will happen is you will get this. You will get x1 is equal to minus 2x2. So that means if I take this matrix again, so the matrix was 1, 2, 2 and 4. So x1 and x2. So how can it take how can we take what values should be given so that it takes it to 0, 0? So that is, we have to take a linear combination of columns. If you have seen that how matrix multiplication is perceived. Now you take one of this, okay, and then you take minus 2 of this. So if you take one of these and minus 2 of this, or you take 2 of this or minus 1 of this, or something of this sort. So you take 1 of this, 2 of this, and minus 2 of this. That means you take 1 of this and you take you take 2 of this and minus 1 of this. So that means this will be multiplied by 2. 2 multiplied by 1 is 2, and this will become 4. 2 of this, and then once you subtract it, you will get 0, 0. That means the solution of this is, so x1 over here. So x1 will be, suppose, 2, and x2 will be minus 1. Okay, so that means this vector 2 minus 1. 2 minus 1 vector is the vector which one once multiplied with this, which one once multiply 1, 2 and 2, 4. Once we multiply this with once we take this A and you multiply it with 2 minus 1, you will get 0, 0. Why? Because you are taking 2 of this and then 1 of this. You know that if you double this and if you add it to here, so you will get 0, 0. That means this belongs to null space of A. So null space of A has this vector 2 minus 1. Okay, what are the other vectors that are there? So if you multiply these vectors by any constant, say C. So if you take any vector of this form, So if you take any vector of this form, which is say 2c minus c of this form, so any vector of this form will be taken to 0 by this matrix. Okay, so then that means null space of A here contains 1. You know that it will be containing this 2 into c into 2 minus 1. Okay, so c can be 0 as well. So this is the null space of this A. Okay, you clearly saw this. Now you have a space. Initially you had some matrix. So in that matrix, the only vector which was taken to 0 was a 0 vector. So second time you saw, okay, there are some values. There is a line. So this whole thing represents a line in R2. So if this is R2, so this 2 minus 1 is a line. Okay, it represents a line which goes to the origin. Say this is the line. Say something of this sort. 2 and minus 1. Okay, 2 minus 1, whatever. I didn't make the line perfectly, but you know that this is you have to keep one value as positive. That means x should be, say, positive and y should be negative. So that means some points which belong in this. Say let's not draw it exactly. So you know that you can just have these and you can draw the exact line. So let me have any line which goes to the origin. Consider this is the line. Okay, sorry for the drawing. So what I'm saying is that there is a null space, that is there is a set of vectors, so which once applied, once this A is applied onto those vectors, so when you apply these A vectors onto them, so all these vectors which belong to this line, they are crushed, they are brought to this 0 vector. So the 0 vector is the origin, they are brought to this origin. But in the first example, if you saw, there was only one vector, that is 0 0 vector. Other vectors were not taken to 0 0. That is null space. In the first example that I took, the example first was this. The only vector that we had over there was 0 0, that is 0 vector. We had only one vector that was there. But in this example, the second example that we have, so here we have a line of vectors, that is, this is a line of vectors that are taken to the 0 vector. The null space of A is not just 0 vector, but it is a line of vectors. So what is the difference between this? So if you sort of see these things carefully, okay, if you take the first example that we saw, so first example was this 2 0 0 3. So if you apply, say, Gaussian elimination on this, or if you just eyeball it, so you can clearly see, because you have seen a lot of matrix multiplication, you have seen a lot of perspectives on the matrix multiplication. What you can clearly see over here is these columns are independent. Okay, that means independence basically means information. So if you see from deep learning perspective, so whenever you see something is independent of other thing, that means whatever this information is there, in this column you have some information, in this column you have some information. That means if there is independence in these columns, that means they carry different information. If there is if one column can be brought from other column, and if they are linearly dependent, that means there is a redundancy in the information, you can remove some of them. So now you saw that these two columns were linearly independent. Then you can clearly see that the null space basically was 0 0. That is, no information loss was done by this matrix. That is, no vector was taken except 0 vector, no other vector was taken to the 0 0. Okay, so you can see over here. But if you see the other, if you eyeball this, the second example that we did, you see the first column and the second column are linearly dependent. Okay, that is what you can see over here. There is a bunch of vectors. So there is, initially if you see null space here was 0, so it was only taking one vector, that is 0 0, which was in the null space of A. But in the second case you saw that these two were linearly dependent on each other. So what you can see is there are a bunch of vectors that lie on this line. Suppose this line is that line 2 minus 1. So this line is the line where if you have these vectors, once you apply this A onto these vectors, so they will land at this 0 place. That means null space of A is not just containing the 0 vector, but a line of these things. Okay, but what is the thing that we ascribe it to? That is this linear dependence. These two vectors, that these two columns if you see, or rows if you see even, so rows in this case are also linearly dependent. So linear dependence somehow creates the problem. So it's not the problem is not that we're just losing information from deep learning perspective, but you can see what is contributing towards this null space. So why are we getting some more vectors? So what you can see is if you get more vectors in null space, that means there are a lot of the vectors which are taken to this vector 0. So such matrices, so the information content of such matrices is basically less, so they don't preserve much information. So once you apply that A onto these things, it takes majority of the vectors to 0. So if null space is bigger, so what you should sort of think about this, if you have bigger null space, by bigger I mean that is you have a lot of vectors in this, by lot, so you don't have just this line. Probably sometimes if you are in, say, R10 10 dimensional, so here you are in R2, so R2 dimension you had this line, one line was there. So but if you are in R10, say if you have R9 dimensional, some line was there or plane was there which was taken to this 0, that means if there are a lot more vectors in this NA, that means this matrix has is taking a lot of vectors to this this null space. That is, if you give that information to this matrix, so it is transforming them and it is it's collapsing that information to 0. Okay, you should be very careful. And such matrices, once they appear in deep learning, if you have a notion of this null space, okay, this is a matrix, I assume that the null space of this will be huge. That means it will take a lot of vectors to this 0. That means there will be a lot of information degradation. Okay, any questions so far? So the first thing that we will see is that if you see this null space of A, so null space of A can be seen under different light when you are seeing deep learning. The first thing you can see is, suppose if you have a matrix A, and if null space is bigger and bigger, that means there are a lot more vectors of null space, and that means this matrix A is taking a lot of vectors to this 0 vector. That means there is a degradation of information. By this I mean a lot of information that was there, so you wanted to transform this vector into something else and you wanted to do something with that. But what happened is, maybe in between the layers, because all these layers if you see, so you have these hidden layers, in between them you have these weight matrices and you have these biases. So weight matrix, once you perform this aggregation or you do that affine transformation, so you are actually applying a transformation on that, the affine or linear transformation we call it. Then you have this n of a. If null space of a, that means there are a lot of vectors which are taken to 0 by this a. There will be a degradation of information. The more vectors are taken to a, that means this matrix is not good for us. But second thing you can see is there is an opportunity to reduce. A reduction is there, so you can do reduction. So what do I mean by reduction? Suppose you have a matrix, it is doing a very good job, but this matrix is very, very big. But once you saw it, once you saw the matrix closely, you saw, oh, this is taking a lot of other vectors to 0. And I have to do a lot of computation in order to arrive at the result. So can I do something? Can I sort of replace this bigger matrix which has this n of a huge? Can I replace it with smaller matrix? Smaller matrix. There will be a lot of information obviously, but what you can do is, suppose you had matrix, you reduced it to 10x. Okay, 10x reduction was there, and your loss of information was hardly from 100% to say 98% loss information was there. So you had only 2% information loss. So you initially had 100% information. Now you have 98% information preservation. That means your effective loss is only 2%. So you are reducing matrix by 10x. Okay, you're only getting 2% loss, and you will see, okay, in some applications this 2% loss is okay, because now my computation is very fast. I can perform this computation very fast. So you see opportunity and you see the problems as well once you see this null space. So this is, as a deep learning person, this is what should get into your head. The second important thing that we discussed was, suppose whenever you see this deep learning or machine learning, so what you do is you have these points, you have these features. Everything in deep learning or machine learning is represented by some numbers. So you have these numbers 1, 4, 3, and you might have seen that we have word to vec, even words have numbers. You have numeric data that is inherent numerical, but you have these words which are numbers. You have spectrogram which are numbers. So whenever you make a data point, so let's suppose you have this X matrix which is having your data. So each row here, suppose you have this R1, you have this R2, each row is a data point. Okay, and this is a bunch of number. If I take R1, if I zoom it on it, so you can get something of this 0.2, 0.5, something of this sort, 0.9, maybe 1.4, something of this thing will be there. And this is your data point which is numerically represented. Now if you see it from a lens of linear algebra, so what we can see is, suppose you have an image. So your image is 28 cross 28 pixels, that is 784 pixels, and each pixel is represented by a number. That means you have this image. So image I, it belongs to all of these, let's say, are real numbers, so it belongs to 784 dimensional vector space. Now so let's say you are doing MNIST classification. By MNIST I mean you have those handwritten digits where you have 0, 1, 2 till 9, you have 10 labels and you are classifying them. So now your goal is you will be given this 784 number, that is you have some vector which is lying in 784 dimensional vector space, and you have to downgrade it. You have down projected rather than downgrade, you have to down project it to some R10, some 10 dimensional space. Say if I can maybe use a trick, I can say, okay, this is my R 784, which though it is not, it is 2 dimensional space. So what you can say is, okay, each of these, because it will form some clusters over here. Okay, so there will be some data points over here. Okay, so these will be some data points. So once you see these clusters, what is the job of a neural network is, okay, can you somehow do this mapping into this R10? If I can have R10, suppose in this R10 you will have 10 dimensional space and you have basis vectors generally. So this first basis vector is 1, and then you have all zeros. This is your, suppose this represents your 1. So suppose all no, this represents your 0, sorry, if you have, and then 0, 1, then all zeros, this represents your 1. Similarly, basically if you have a vector which is like this, EI, ith entry is 1 and rest of 0, that means this is that if suppose if EI is 1th entry, first entry, that means it is number 1. If it is second entry, it's number 2. This is basically one hot encoding, that you know what that is. So these are your basis vectors in R10, and you know this is the basis vector. So what you are trying to do is, you are trying to take this data from R 784 dimensional vector space and you are trying to collapse them onto one of the basis vectors. That's what you are trying to do in this matrix manipulation. You are applying non-linear activation function, whatnot, and you are doing a lot of stuff in between. But if you see what is the starting goal and end goal, you have a huge vector which lies in 784 dimensional space. So what you have this R10 now. So R10 is a 10 dimensional space, but what you are trying to do there is, you are trying to collapsing each of this vector. So you have an image over here. Suppose this image is of digits, suppose 1, something of this sort 1. So you want to collapse it over here. You want to collapse it in this basis vector, in this standard basis. So you have this 0, 1, 0, 0, 0. If you see, this is a standard basis in R10. So in R10, what could be the basis vectors? So you know that you will start from this and you will end at, suppose you have this such 10 vectors and you will end at this. So once you see this image 1, which was initially in 784 dimensional space, all the image that are of these ones, so that they should land at here. They should land 0, 1 and all zeros. They should collapse somewhere here. So that is what this is doing. This is doing a transformation of these vectors rather. So now how do we relate this null space over here? Suppose if you initialize your network and your network has such an initialization where most of these weights are dependent on each other. So the weights, you know that they have to do transformations. So now if they are dependent, so that means they are not doing anything new. So they are taking much of the vectors. They are either, suppose if this null space is huge, that means that you have a lot of dependent vectors in these matrices that you have in between these layers. So once you apply that, it is taking many of these vectors to 0. That means your learning will be slow. So your gradients, once they are flowing in the backward propagation, so what will happen there is it will have to work hard to get those gradients right. Okay, so it is better to initialize networks such that these initializations, the vectors, the matrices that are between layers, so they should have independent information, so that once they are transforming the vector, so they are contributing towards doing something, not just taking the vector and boiling it down to 0, because getting something out of 0 is almost impossible in matrix notation. If you have, suppose a x is equal 0, some x vector was taken to 0, so can you do something with this 0 now? Because you know that you will apply the transformations continuously. You will apply first transformation, then non-linearity, transformation, then non-linearity. So once you have the 0, it becomes difficult now to extract much more any more information from here. But it also has a positive side, because sometimes you want on purpose to have some layers where you want to say, okay, I want these neurons not to learn anything, because you know that we have the problem in neural networks that's called as over parameterization. Okay, so what is that? That means we have a lot of parameters. So there is a high possibility that this overfitting will happen, because a lot of parameters are there. So if we give the data, so our data will be memorized. It will not be, the network will not generalize it. So there sometimes you want on purpose that in each of the iteration, all the layers should not be trained equally. So you want that some layers should be trained, some weights should be trained in a way so that they get trained in one iteration. In the other suppose iteration, you want, oh, this should not now be trained, some other weight should be trained. So that time you want this A in such a way so that in that sort of a layer you want it sort of take many of these vectors to 0, so that it is not trained in that iteration. Okay, you can see a lot of implications just from this null space. Okay, let's go ahead now. Now we'll take another example. The two examples the first example we saw that there were the columns were independent. Now the second example we saw that columns or rows were dependent. You saw that now null space of that matrix had more vectors. And now we'll take another example and we'll see what are the consequences of that. And then the question will be, is there an algorithm by the help of which we can find the null space of any matrix? Okay, let's take this example A. A is equal, say example, this is 1, 2, 1, 2, 4, 2, 3, 7, 4, 1, 3 and 2, something of this sort. Okay, here you have M is equal 3 and N is equal 4. So now this is our A matrix. So now what you can see from here is, how can I sort of see are their columns dependent, independent? So we will use an algorithm. We'll use Gaussian elimination. So we'll have pivot rows and then we'll try to make 0, because we are solving AX is equal 0. Okay, now if you see, if I am having AX is equal 0, if I perform row operations on this, if I perform elimination on this, suppose I'll get some UX is equal 0. So you know, for this U and for this A, null space will remain the same, because I'm not doing any trickery. So I'm doing A is being converted to U, and you know that this X will still remain the same. That is, null space of A will still be equal to null space of U. There is no change in null space. Column space we'll have to see, is column space being changed. So if you are performing the row operations and you are converting from A to U, so maybe the question is column space being changed? Could be and could not be. You'll have to see that for yourself. But if you see clearly, null space will remain same. So whatever vectors we had in X, so whatever vectors in this first case were taken to 0, same vectors will be taken to 0 over here. Why? Because we are not changing the solution of the equation. The solution of the equation is basically values of this X. So null space of A will remain the null space of U. So what we can do is we can apply Gaussian elimination over here. Let's do that. So once you take this matrix, so you'll perform the operations. So you have 1, 2, 1, 2, 3 and 1, 2, 4, 7 and 3, 1, 2, 4 and 2, something of this sort. Now you saw you have three of these rows and you have 4 of columns. Now you know, because we are working on R3. We are working on R3. So 3 vectors should have been enough. So if you only had 3 independent vectors, that was enough to sweep or span the whole R3. But you saw that we have one additional vector. For sure, one of these columns, if you see, will, like, one of these can go to 0. That means there is some dependence. That can be clearly seen. Why? Because if we are working in R3, so if you take these columns, so we had only 3 columns were enough to, if they are independent, they were enough to sweep or span the whole R3. But you have this 4th column now. Now for sure you will see that. So there is a possibility that one of these columns can be redundant. Now once you do this, so what I can do is I can convert, I can apply Gaussian elimination on this. You know what operations to perform, how to do that. I won't do that. So first pivot is this. So let's say you have the first pivot entry, that is over here. So this is your first pivot entry. So below this you will have to make all these entries equal to 0. So what you do, you know what to do. You have to multiply this and that, and I'll just write the second step. So what will happen because of this? So once we do that, so matrix becomes 1, 2, 3 and 1. I'm not doing anything with this, but I'm doing things with these two things. I'm making these entries 0, 0, 0. And how these columns are getting changed is like this. Okay, this is the step 1 in the Gaussian elimination, because you are using this pivot and making these entries 0, and you have to perform row operations. And what row operations are you performing? You will multiply this with something. You'll multiply this with 2, suppose, and you will subtract it. You'll subtract it directly, and you will get this. This is the step 1. Step 2 is, now you saw this. So you had first pivot was here. Okay. Second became 0. Now you'll use this. Okay. And once you use this as a pivot now, because this entry was 0, I could have swapped it, but beneath it was also 0. So I was forced to use this. Now I will make beneath it as 0. So step 2, once I perform that, so I'll get 1, 2, 3 and 1, and I'll get say 0, 0, 1, 1, and this will be 0, 0, 0, 0. Why? If you see, these two rows are pretty similar. So now you can see clearly over here, this is sort of upper triangular matrix, let's say. Not exactly upper triangular. So this is actually called as echelon matrix. These matrices are called as echelon. Why echelon? Because they are like stepwise. So if you see over here, they are something of steps of this sort. That's why they are called as echelon matrices. So now if you see over here, so one of the whole row became 0. So if this became 0, what I can do is I can do the back substitution. Okay, I can now use backward, or I can also eliminate like in the backward way. So this was my first pivot, this is my second pivot. I can also perform backward elimination, and then I can use the substitution. Let's do that also. Let's make these entries 0 as well. So what will happen if I perform step 3? Step 3 will be backward elimination. I was doing forward elimination. Let's do backward elimination. Backward elimination means, so whatever pivot you have, you make the above entry 0 as well. So let's do that also. Okay, once you do that, the value that you get what is 1, 2, 0 and minus 2, and this is 0, 0, 1 and 1, and this is 0, 0, 0 and 0. This is what you get after you performed the backward elimination. Okay, so as I told you, these are called as echelon matrices. So what one more thing that I can do over here is, maybe I can directly from here I can use substitution. I can find the answer, or I can do one more thing. I can make this identity matrix. Okay, if you see over here, what I can do is I can make this pivot. This is already 1 actually. Okay, so if you see this pivot over here and this pivot here, luckily were 1. Okay, sometimes they might not be 1, so you'll have to make them 1. Okay, so for those matrices we call them as row reduced echelon form. Row reduced basically means you are reducing these rows to 1. Whatever these pivot entries were, you are reducing them to 1 as well. So such matrices are called as row reduced echelon form. So this form over here is called as row reduced echelon form. Now if you see, so this is our pivot column. Okay, this is also our pivot column. These are our columns. So now if you see this is say our x1, x2 and x3. Okay, and this is equal to 0, 0, 0. So now if you expand this, so you clearly see the x3 is 0, and now what you can do is over here, so from in the first you can say x1 plus x2 minus 2x, this is actually, this should have been, this is 1, 2, this should be x4 also, because 1, 2, 3 and 4. So x1 plus 2x2 over here, this is 0 times 3x3, and this is minus 2 times x4. This is equal to 0. And this, if you see second thing, so over here you will see x3 plus x4 is equal to 0, and in the last over here you will see this whole thing becomes 0. Now you have these two things over here. So these are the two equations that we reduce it towards. Okay, now if you see these pivot entries, so this entry over here and this entry over here, so they are given forced values, and these variables over here, so this is corresponding to suppose x1, okay, and this is corresponding to say x2, and this is corresponding to x3 and x4. Now you have these 4 columns, each the column is corresponding to one of the variable. So these are our pivot entries, and now these variables are called as free variables. These variables, they're called as free variables. So what we can do is, so you have this x1, x2, x3 and x4. So you have these 4 entries over here. So you have 4 columns. So now you know that x1 and x3, they are pivot variables. So this x1 and x3, they are pivot variables, because we got them because we had the pivot in that column. But this x2 and x3, they are free variables. This x1 and x2, they are free variables. So what you can do is you can give free variables any value, and then you can find x1 and x3. Let's see what we generally give them is, so x2 is equal to 0 or 1, and x4 is equal to 0 in one case, and in other case what you can do is you can say x4 x2 is equal to 0 and x4 is equal to 1. Why? Because these two, there are two entries. Now what I do is I will give them standard basis in order to find the solution. So now if I give this value, if I say in the first case 1, this is my case 1, this is my case 2. I'll again try to summarize it later on, but if you have questions, please pay attention here. So once I got this row reduced echelon form, what I found is that we had some entries became 0 and we had less pivots. Okay, less pivots were there. Now these pivot entries that you have, that they correspond to x1, this is correspond to x2, x3 and x4. We have two pivot entries and we have two free variables. We can give free variables any value. So but what I'm saying is I have to make a combination of values. So why not to do one thing? If I have two free variables, I'll give 1 and 0 and 0 and 1, because I know if this is like R2 and these two vectors are basis vectors in R2, they can span the whole R2. So if it was x3, if there were three entries which are free, I would have given them 1 0 0 0 1 0 0 0 1. But here we had only two free variables. Now what we can do is we can try to solve this. Now if these are given values x2 and case 1, let's solve it parallelly. x1 and x, these are given 1 and 0. x2 is 1 and x4 is 0. x4 is 0, so this is becoming 0. Okay, that means x3 is 0. If x3 is 0, x3 we have already done that. x2 is 1, so x2 is 1, so we'll get 2 over here. So this will get 2 over here. So now the question is we'll have, and x4 is also given 0, this will become 0. So x, if you see in this case, will become minus 2. x1 is equal to minus 2. This will become minus 2. Okay, in this case. So in this case you have these entries. So you'll get some values corresponding to these x1. You'll have to find x1, x2, x3 and x4. So what you are trying to do is you are trying to have these free variables. In our case, x2 and x4 are free variables where we are giving them values. So the values that we give them, suppose initially we are giving them say 1 and 0 and then 0 and 1. So correspondingly you will get values for x1 and x3. Let me do that. Let me find the values. This is a special solution. So the special solution 1 basically is, so S1, special solution 1, once we took this 1 and 0, that will give you solution as minus 2, 1, 0 and 0. Okay, in case of S2, special solution 2, that is once you do 1 and 0. So what will it give you? It will give you 2, 0, minus 1 and 1. Okay, if you see, these are free variables. I think free variables were x2 and x4. So if you see, these are x2, okay, these are x4, these are x2, these are x4. So initially in the first special solution, this was 1 0 and this was 0 1. So once you solved it for the x1 and x2, x1 and x3, so you got minus 2 and 0, you got 2 and minus 1. Any questions so far? Any doubts? Any questions still here? Now what you clearly saw over here is this is your S1 solution and S2 solution. This S1 is the solution once these three variables, they were given 1 and 0 values. Okay, this was your x2 and this was your x4. Okay, and suppose this over here was given now as minus 2 and this you got as similarly as 0. Similarly in this case you are given 1, you are given 0 and you are given 1. So now you are finding value for this, you are finding value 2 and minus 1. Now you got these two solutions. So if you have a look at the matrix, okay, let's again write the matrix and I'll show you these two things are taken to 0, because I told you if you have a matrix A and if you have X and this is taken to 0. Now if you change it to some, let's say R matrix, row reduced echelon form, and this is again X and this is equal to 0, null space of A will still remain the same as null space of this. Okay, null space of A matrix will remain equivalent to null space of this R matrix. Both of them will have equivalent null space. Why? Let's see that. So initially what we had is that we'll write the initial matrix. The initial matrix was 1, 2 and 1, and then we had 2, 4 and 2. This was 3, 7 and 4, and this was 1, 3 and 2. This is our initial matrix. Okay, then the values that we got. Okay, the values we got minus 2, 1, 0, 0, minus 2, 1, 0 and 0. Okay, see this. So you have to take this twice. Okay, and then you have to take one of this. If you see, you have to take 2 times this and you have to take one of this and subtract them each other, and nothing of these two things. So now if you see this and this, they are double of each other. Multiply this with 2, you will get 2, you will get 4, you will get 2 over here. That means this thing is this thing over here, second column is double of column 1. So once you multiply this with 2, Okay, then you subtract these two things from each other, so you'll get 0 0 because you're anyway taking 0 0 from here. Okay, that's why you are seeing that this is a solution. So this vector belongs to null space. Okay, now what is the other solution that we got? Other solution that we got was 2 0 minus 1 minus 1. This was other solution. This was the first solution. The second solution that we got 2 0 minus 1 1, something of this sort. Okay, let's see. You are taking two of this. Okay, and then you are subtracting them from each other. So let's say you have 3 minus 1 is 2, if this solution is correct. So what will happen as a consequence of this? Basically, you'll also get 0. So this vector and this vector, if this is true, if my calculation is correct, so you have some vector, you have the vectors. I'll write them again. So if the vectors are correct, I will not perform the calculations because calculation. So I got this minus 2, 1, 0 and 0, 2, 0, minus 1 and 1. So these are the two vectors that I got, which are taking this x. Suppose this is my v1 and this is my v2. So both of these vectors are taken to 0 by the matrix A that we had. The matrix A, so this was in the column space of A and this also was in column space of A. Now you know that I can take any linear combination of that. A linear combination also will be in the column space. So you can take alpha of this and you can take beta of this. So once you add these two things together, you can say this whole thing that you get out of this belongs to null space of A. That's how you get the null space. Okay. Now what you can do is you can write algorithm for it. So if you have to write the algorithm, I'll write the algorithm. So let's write the algorithm for this, and then we'll have to code it. The algorithm would be like this. The initial thing that we have to do is you have to take the matrix and perform the elimination, and then you have to get it in the row reduced form. After that, once you get in the row reduced form, you can have these like free variables, and you can have these pivot variables, and you can have free variables, give them any value, and for these pivot variables, you can get the value out of those. Okay, let me just write the algorithm step by step. Okay, I have written over. The first thing is step 1, compute by elimination RREF, row reduce echelon form of A. Okay, so you are reducing A to this R because you know null space of A is equivalent to null space of R because there is no change. Okay, so after that, what you can do is this point number second, you have to identify the pivot columns. So identify the pivot columns. That I did. Oops. So identify the pivot columns. So once you identify these pivot columns, basically pivot columns are those where you have these leading ones. So wherever you find a leading one, so that column will act as a pivot column, and then rest of the column will be free columns, and rest of the columns will be free. Rest of the columns will be free columns. Okay, so wherever you have these, there will be pivot columns, and rest will be free column. And then what you can do is, let's suppose this is your step 3 will be, so let R be the number of pivots. Okay, so you have R is your number of pivots. R is equal to number of pivots, because you can keep track of this R and R also. And so what will be the number of free columns then? N minus R. So how many rows you had? Okay, so you had these n rows, sorry n columns, and then you will do n minus R, and whatever you remain, so these many number of columns will be free columns. Okay, so this will be your free columns. Let's denote it by say free columns. So we have these free columns. I have not given any notation for this, so this will be n minus R. You have n columns in total, and you have R columns as pivot columns, and then you have this free columns. This is your step 3. You have to keep them because you will sort of need them somewhere. Step 4 will be, now what you can do is you have to set free variables. You have to set one free variable as 1. Okay, because you have, suppose you have 5 free variables. So what you can do is set the first as 1, all the other as 0. Set the second as 1, at all other 0. So you will have to run a for loop over here. So for all these, for each of the free columns, so what you can do is you can construct a special solution. So each of this will construct a special solution. So S1, S2, this will be a special solution in which you will keep one variable, one free variable, the first free variable. Suppose in each iteration you have suppose 5 free variables. So you'll have 1 and then 4 zeros, then 0, then 1, then 3 zeros. Similarly, you basically try to create basis vector. So once you get that, and then you have to solve for other variables. So whatever variables are left there. So once you set that free variable is equal to 0, so you can solve it for others, and then you can solve Rx is equal to 0. Okay, for the pivot variables, and then you do the back substitution, and they will you'll get a resultant vector of that, and you will get all these vectors. You will get, say, if you have suppose n cross n, you have this vector space in which say R is number of pivots, number of pivot columns, say. Okay, what will happen is, so you'll have say n minus r as free variables. These will be your free variables. So once you have these many free variables, so you will have corresponding special solution 1, S2, S3, something of this, I'll say, and you can clearly see, you can clearly compute that, and then you can say you can take linear combination of all of these, you will get null space of that A. This is the algorithm. Okay, whatever is the span, basically span of this. So span of all these special solutions. So you will take linear combination of all of this. That means span of special solutions. So whatever special solutions you get, okay, so they will be called as null space of A. So this is the whole algorithm. So in which you saw one important thing, that is R. This is the number of pivots, and you might have heard about a term called as a rank. This is called as a rank of matrix. So what is rank? So once you have a matrix and you row reduce it, and you get a row reduced echelon form. So in that you will find, so how many which columns are the pivot columns. So number of pivots is equal to rank. Okay, so we'll have a detailed discussion on rank. So I'll stop today's discussion over here. I'll take your questions if you have.